All right. So this is lecture 7, and today is the inauguration day, right? All right. So let's see where we are. We've been talking about the concept of couples, okay? And I also, based on that concept, I introduced the concept of equivalent systems. So what I'm going to do today, I will do just a few problems on these topics. I've done a few problems on couples, so I'm just going to do one more problem, a 3D problem, and then I would do more on the equivalent systems by, again, reintroducing it. So just in case if you don't recall that from the previous discussions we've had. So I will start with this problem. It's a very good couple problem in 3D. So this is the problem, okay? We do have an object, okay, that looks like this. So we have a 3D object like this. All right, these dimensions are given. This is 0.16 meter. This side is 1.144 meters. This side is given 0.192 meters, and the length of this inclined side is 0.24 meters. Okay, so this is X, Y, and Z axes. We have two sets of force couple system applied, one here on XZ plane, okay? One of these forces is along X axis, its magnitude 12.5 Newton. And another one is applied this way. If you take the midpoint of these two sides, that is at let's see, 0.12 meters here, this is 0.12 meters. If you take this midpoint, which I call that point F, and this point N, we have another couple. Let me also label these corners A, B, C, D, and E. We have these couples that act like this, along a line connecting this tip to the midpoint, this tip to the midpoint, okay? And this force is 50 Newton. So the problem is asking us to find the total moment generated by these two couple systems. In other words, this represents a moment, right? And that moment is obviously perpendicular to plane of XZ, and this is rotating this way. That means would be acting in the negative direction of Y. And then you have this couple that is generating also a moment, and this is going like this. So that moment would be perpendicular to this plane and acting outward. Okay, any questions so far? No? So let's start with the more difficult part, which is finding, actually, let me start, in the other section, I started with this one. Let me first find the moment that this force generate. In other words, the moment that that 12.5 Newton couple will generate would be what? You have the vertical distance between these two forces. It is rotating this way, acting downward. So that will generate a moment which is in the negative direction of y. That's why I have this as negative, okay, meter. So this moment would be, okay, would be negative, if you calculate that, would be negative 2.4 Newton meter J. So that is the moment of this couple. Any questions on that? No? All right. How about these two? If you look at these two, okay, all I need to do to find the magnitude of the moment that these generates, I need this vertical distance between them, right? So in other words, I need to know what is this D, okay? How do I find D? Let's look at this triangle. So I'm going to redraw this triangle in 2D here. So in other words, this is that triangle. This is NBF. Can you see that? So if that's N, this is that triangle, that D would be, in other words, this force is that 50 Newton, and this is the distance, which is the height in this right angle triangle, okay? So this is D. And these sides are given. This is 0.16, this is 0.12 meter. Any problem with the geometry here? You can visualize that, right? So what is D? All I need to do, if this angle is beta, I can find tangent of angle beta. Tangent beta would be 0.16 over 0.12, and that gives me the angle beta comes out to be 53 degrees. So if this is 53 degrees, I want to find D. I look at this triangle now, okay? This is a right angle triangle, okay? So D would be what? D would be, in this triangle, if I write the sine of beta, that would be D over 0.12. I have beta, that gives me D, which comes out to be 0.096 meters. Okay? So the magnitude of the moment that these two couples generate is what? I write that this way. Magnitude of that 50 Newton couple would be what? Would be 50 Newton times D. So that would be, and D is 0.096. So that would be 4.8 Newton meter. That's the magnitude of that. But I want to have the vector equation for this couple because I want to add it to this to find the total uh, moment, right? So this is how you set that up. Let me, this is a magnitude of a vector that is perpendicular to this plane and obviously going upward, right? So if you look at this plane from this direction, okay? In other words, if I look at from this x-axis. I see this plane will be just this line, right? B, D, and C. This is B and A. Okay, that is that plane. And this moment, which is 4.8 Newton meter, acts upward in that direction, perpendicular to this plane, which is this plane. Can you see that? Can you visualize that? So if that is this vector that represents this moment with this magnitude, how do I find the components of this? I have the magnitude, okay. Let me call this angle alpha, okay? So if this angle is alpha, first of all, if you, I can find that alpha because this is 0.192, this is 0.144. So tangent of alpha would be 0.192 over 0.144. And it happens by accident that alpha comes out to be almost the same, 53.1 degrees. Okay. But why do I need alpha? Because if you look at the two components of this moment, right? This is m along y direction. This is m along z direction. That's what we want. This would be the projection of this along y. This would be projection of this along z. But what is this angle? This angle would be also alpha. Why? Just a little bit of geometry. If you have an angle alpha, okay, you have another angle that its sides are perpendicular to the sides of this first angle, okay? These two angles would be equal, and that's what we have here. So mz, its magnitude, would be that 4.8 Newton meter times cosine alpha, and m sub y would be 4.8 Newton meter sine of alpha. So I have alpha. I can calculate these. You get m sub z that comes out to be, I'm sorry, m sub z, yeah, that comes out to be 3.84 Newton meter, and this one comes out to be 0.48 Newton meter. Therefore, that moment of the 50 Newton meter has these two components, can be written as 0.48 J plus 3.84 K. So this is the other moment. Okay, so this is the first moment we found. This is the second moment. So the total moment, which is what the problem is asking, would be M1 plus M2. If you add these up, you see that it comes out to be 2.4 J plus 3.84 K. That is adding the Y component here and K component here. So this is the answer. But the problem is asking you to find the magnitude of this, which is easy. The magnitude of this moment, total moment, would be the square root of 2.4 squared plus 3.84 squared, and that would be 3.22 Newton meter. Okay. Any questions? Let me pause here.
So when you were adding the M1 and M2,
Mhm.
why did you not have to use the J from M2? And
I did.
also, why did the 2.4 plus or negative 2.4 plus 0.48 became 2.4?
Oh, sorry about that. Yeah, no, I think I made an error here. I wrote these down. Uh, um, you know, these should be actually 4.8 J. What? Not four. I don't know why I wrote it down like this. This should be. Let's see. Okay, the outcome would be this. I wrote it wrongly. So the 4.8. Okay, that would be this actually. Total moment of for 50 Newton is this. Okay. And for that one, I added, okay. So what happened? Negative 2.4 J, and this one is, no, I have this somehow wrong. I did it in the other class, I had that right. So moment of the 50 Newton comes out to be 0.48 plus 3.84. Moment of this comes out to be this. And so we have 4.8 J minus 2.4 J. So this is 4.8, not 0.48. So this is 4.8. Sorry about that. So that's why some of them comes out to be 2.4. So this is 4.8, because this is almost equal to 1. So 4.8 Newton meters. Okay. All right. That's where the problem was. Thanks for asking that question. So this is positive, this is negative, total would be this. Any other questions? So if not, let me do another, let me now move to the main topic that I want to focus on today, and that is the equivalent systems. The concept of equivalent system is really lays out the foundation for what we are going to focus on, and that's the foundation of statics, and that is rigid body equilibrium. But what is equivalent system? You remember last time I said that if you have a force acting at any point on an object, you can simply move this force to any arbitrary point you want, okay? And in order to do that, you just have to add the moment that this force generates about this new point and put that there also. So what we're saying is that if you have a force like this force would do the same thing to this object as this force and this moment do. The function of these two acting on this object is the same. We call these equivalent systems because the action of this force here and this force coupled here is equivalent, is the same. And of course, we proved that. How we came up with this. If you remember, I said that in order to move this here, I just consider that I have put a force here in the same magnitude in opposite directions, but these two end up being a couple. So that's why you ended up with this. So we want to demonstrate the application of this equivalent systems through two examples today. Okay. So I'm going to do two examples. One would be a 3D and the other one a 2D. Okay. So let's do that. Okay. Let me start with a 3D problem first. Okay, this is that 3D problem. Let's say, and this is also an example from your book, 3.97. We have a door, okay, hinged here and hinged here. And this is a doorknob. In order to hold this door in place and not letting it to open up, we have put a piece of stick here. So let me call this point A. Coordinates of all these points are given. So the doorknob, this is X, Y, Z, is at a distance of 0.99 meter from the floor. Okay, this distance is 0.1 meter. This distance is 0.594 meters. And this doorknob is at a distance of 0.067 meter from the y-axis. And this hinge is at a distance of 0.75 meters. And it is located at a height of 1.85 meter from the ground. So the problem states this. It says, if the force in that this stick is generating, okay, the force that is acting along this stick, which I call that F, if the magnitude of this force F is given, 175 Newton, find an equivalent system at point C. That means moving this force to point C, which results in generating a moment, which is the moment that this force creates about point C. That would be, in other words, what we want to do, we just want to simply move this force F, put it here, and we know that is going to cause a moment that would be generated in these three directions. And I want to find that moment. Is the problem statement clear? All right. So the first thing is, first of all, what is the vector equation for this force? Because I need that to find its moment about point C. That would be magnitude of that times the unit vector of A, B. What is unit vector of AB? Let me write down the coordinates of these points. This is negative 0.067, y of 0.99, and z of 0. Point A is at negative 0.1, y of 0, and z of 0.594, and I also need the coordinates of point C. If you calculate it based on all these dimensions given, you see that comes out to be 0.817, 1.85, and 0. Okay, so I can easily find then unit vector here, tip minus tail, that you calculate that, you see would become 0.33 I plus 0.99 J minus 0.594 K divided by square root of all these 0.33 squared plus 0.99 squared plus 0.594 squared. That would be 1.155, and this gives me the force vector equation for that to be 5 Newton I plus 150 Newton J minus 90 Newton K, or I intentionally write it like this, okay? I plus 30 J minus 18 K. So this is the vector equation for the force. So I can simply put this force here, just move it here to create an equivalent system. I need to find the moment of this force about this point and put that in there. That means I need to find the moment of this force about point C. What does that mean? I need to find a moment of this force about point C. So I need to set up a position vector connecting that point to any point along this. I would prefer this as the position vector because it's a two-dimensional vector instead of this, which will be a three-dimensional vector. So I write that as CB cross F. But what is CB? Tip minus tail. If you subtract these respective values, you find this to be 0.683 I minus 0.86 J. So this moment of this force about C, okay, would be evaluated by setting up this determinant, 0.683 negative 0.86, 0. Force is 130, 18. If you expand this determinant, you will get 77.4 I plus 61.5 J plus 106.8 K, all in Newton meter. Okay, so this is the moment that will be generated as a result of moving this force to this point. In other words, this moment will have, if this is point C, will have three components, all of them positive, causing positive rotation along X, along Y, along Z. Okay, so this is X, Y, Z. Any questions?
Hey, Professor, how did you get vector CB?
Oh, you mean the vectors? How do I set this up? Right?
Yeah.
Well, vector CB would be what? Tip minus tail. So negative 0.067 minus 0.817. I see what you're saying. You're saying that why this isn't negative, right? And the reason for that is this was actually negative because So that's why 0.0 minus minus then becomes positive.
Oh, I see. Okay, perfect.
Oh, thank you because I hadn't noticed that this should have been negative. All right. Any other questions? No. All right. So let's move on to the 2D problem. So I want to do a 2D problem, equivalent system. So this is an example again from your book. Let's say it's a simple example, but it introduces a very important concept, and that is this. Let's say you have a beam, okay, and you have these two forces, 300 Newton, 200 Newton, and a moment of 400 Newton meter acting on this beam. What I want to do, and that's what the problem is asking, is to find an equivalent system at A. What does that mean? That means move everything you have, move it here. These two are already at point A. Actually, I would extend this problem. Find an equivalent system at A and B. How about that? That means the first part is I want to move everything to point A. So this is point A. I have this force here already. And this distance, by the way, is 3 meters. And I have this moment here already, right? So I just simply move this force and put it here. But to do that, I need to find the moment that this force generates about point A and also add that to this. So what is the moment that this force generates about point A? You have the vertical distance from A to this force. And this is acting this way. So the moment that generates, which is 200 times 3 or 600 Newton meter, will be in this direction. Therefore, the equivalent system of forces that would act here would be 500 Newton and a 1000 Newton meter moment. So what this system does to this beam is identical to the action of this system to this beam. That's why we call these equivalent systems. Okay. How about if I wanted to move everything to point B? What do I do? If I want to move everything to point B, okay, this force is already here. So I need to move this force, putting it here. This is a free moment, so moment can be put anywhere. So that was that 400 Newton meter. But by moving this force to here, I need to put the moment that this force generates about this point, and that would be in the opposite direction, and that would be 300 times 3 or 900 Newton meter. So if you add these up, you will get, okay, a 500 Newton. This is 400 this way, this is 900 that way. So you end up with 500 Newton meter here. So this, and this, they're all the same or perform the same function. And we call them equivalent systems. Any questions? All right. So why do we study the concept of equivalent system? Okay. The whole purpose of equivalence system is to lay out the foundation for rigid body equilibrium. Okay. What is the meaning of rigid body equilibrium? Any structure you can think of, mechanical, structural, aerospace, marine, doesn't matter, okay? They are somehow supported externally by something that is holding them. And these objects are subjected to a bunch of moments and forces that act on this object. What is the principle of static equilibrium? Static equilibrium tells us that this object would stay in equilibrium or it does not move. But what does that mean? This object is subjected to all these forces that are acting externally on the object as loads, and also forces that are holding it from these supports. We know, based on the concept of equivalent systems, that all of these forces and moments can reduce down to a single force and a single moment. So if this object is not moving, sum of all these forces and sum of all these moments has to be zero. This is the meaning of the concept of rigid body equilibrium. Since all forces and all moments acting on an object can be replaced by a single force and a single moment, where that single force is the resultant of all the forces acting on the object, and the single moment is the resultant of all moments that are acting on the object or are generated due to moving those forces to whatever point about which we are considering the summation. These two have to be zero in order for the object not to move. Based on this concept, then we introduce the concept of rigid body equilibrium, which allows us to address two objectives, which are the fundamental objectives for studying statics. What are these objectives? If you have an object, let's say a chair, this chair is supported externally. That's not, of course, a chair. This is a chair, right? All right, that's not what I meant. If you have a chair and you're sitting on this chair or somebody's sitting on this chair, okay? This chair, okay, or this tree, okay, is supported by something. In this case, this chair is supported by these legs that are sitting on the ground. But this chair consists of pieces that are connected together. The objective of static equilibrium is this. As long as we know this chair is not moving, sum of all forces acting on this should be zero. This, and some of the moments. That means by using that concept, we can find all external reaction support forces. We know this tree is not moving. Wind is blowing against this tree. Birds are sitting on branches of this tree. We want to know how much force this support, the roots, represent that are holding this object in peace, in place. That's the first objective, that we are given an object that is supported externally, a bridge, how much force those piers or the columns that support the bridge are subjected to that are holding this bridge in place. This is the first objective. The second objective is how to find internal forces. What does that mean? This chair is made of components that are welded together or bolted together or whatever. I want to know if you're sitting on this, so you're exerting a load on this chair, how much force is developed at the point of connection of these pieces? Or if you want to design this chair, build this chair, what kind of bolts or connections you need to consider to withstand the forces that develop internally at the point of contacts or connection of these pieces. These are the two objectives of statics. Find the unknown forces that are supporting the structure in one place, or find unknown internal forces that hold pieces of the structure together. The rest of the course, that's what we focus on, and that's what we will be doing. So with that said, I'm going to stop here, and let's see if you have any questions. I will answer that. No questions? All right. So if you have no questions, I will see you either during my office hours or I'll see you on Friday. Have a great day.
Thanks, Professor.